Okay, so what we have seen so far is that, at least for the first order system, we know how to draw a Bode plot. I can just remind you what qualitatively looks like, and if you want a quantitative uh, plot, you can use this expression and plot exactly these functions, or otherwise you can use MATLAB to plot it, now that we have nice computational tools. But what I want to do in this second half of the class today is to see, at least for the first order system, how does the Bode plot change when we change the parameters of our linear system. So this is what we are going to see now. So I just grab this expression here for the steady state, I know that my steady state has this expression here, and the Bode plot is nothing but the plot with omega in log scale of the amplitude gain in decibel, and also we have, as the second part of the Bode diagram or Bode plot, the phase phi. So what happens when we take our steady state expression here and we modify the parameters that we have now, that are actually A, B, and C. These are the parameters that we have for our system defining it. What happens if A becomes bigger? What happens if C or B become bigger? How do they affect the Bode diagram? Is it going to be changed in a drastic way? It keeps its shape, and so on. And to do this, we are mostly going to use MATLAB to verify what we are doing, because from a quantitative perspective, we can always plot our functions in. We have an analytic expression for our gain and so on. So if we want to do this analytically, we can always do that. We're using a computational tool just to do this faster. It's not a limitation of the theory. Theoretically, we can answer all these questions. I want you to start gaining some intuition behind the role that A plays, is the most important, I'd say, of all these parameters, and also the role that is played by the parameters C and B. And since they're being multiplied together, you can understand that they pretty much play the same role, because if you make B 10 times bigger, or if you make C 10 times bigger, at the end of the story you obtain exactly the same effect in terms of the amplitude. So the first thing that I'm going to do is to change A. So let's see how we can do this in a nice way. I'm not the best drawer here, so so this is the Bode diagram, and I want to show you the effect of modifying the parameter A. So let's go back to our MATLAB. I have already cleared the workspace and everything. So what I'm going to do is I'm going to define our usual parameters. A is going to be equal to -1. Remember, we need to have stability. B is equal to 1. C is equal to 1. D is equal to 0. So I do this. I define a system as a state space, A, B, C, and D, in this way. So in this way, I have in just one line, I define all the parameters, and I have my system as defined. And as these are exactly the parameters that we used in our example for the verification of the state response. This is the Bode plot of our system S following having these parameters. Okay, as you can see, let me. I think I found actually a good way to avoid to draw things. I'm going to just, let's see if this works. I'm going to simply plot this diagram, and I'll incorporate that in the notes so that we can make a comparison. So let me just print it here. Well, before I print anything, this is the diagram that we have for our choice of parameters. Now what I'm going to do is I'm only going to make A bigger. So I'm going to take the same line, but I'm making A 10 times bigger. I'm going to create a new figure, and in this new figure I'm going to have the new Bode plot. So now we can compare the two Bode diagrams, one next to each other. As you can see, they look absolutely identical. The thing that you have to pay attention to is what has happened to the scale. So here in this scale we have the magnitude that starts when omega is, let's say, very small, when omega is 1 divided by 100. This amplitude is roughly 0 dB, and 0 dB means that this amplitude is equal to 1. And then it follows this kind of behavior. And the phase starts with being slightly negative, close to 0, and then it becomes, the phase here is reported in degrees. I tend to prefer radians for the phase, but it is minus 90 degrees, so minus pi divided by 2. The phase is actually identical, pretty much identical in both cases. What has changed is the amplitude and another thing. So here the amplitude, when omega goes to minus infinity, that, as I remind you, it means that in the logarithmic scale we're going to the extreme left. So when that happens, we have a magnitude that is minus 20 dBs, so it is way lower. And then we have this change in slope, because it stays flat for quite some time, for a certain range of omegas, that is, roughly speaking, these 2 decades, from 10 to minus 2 till 10 to the power of 0, and here from 10 to minus 1 till 10 to the power of 1. So roughly in the same, in a range that has the same width on a logarithmic scale, stays flat, and then we start having a slope. The slope here starts when A is equal to minus 1, starts at omega equal to 1. Instead, then we have this slope, change in slope, here when omega is equal to 10. So the comparison can be made in this way. The phase stays pretty much the same if we are changing our parameter A. What happens with change of A is that we have a lower, much lower amplitude gain, and also this change in slope happens at a higher frequency in the case a equal to minus 10 as opposed to the case when a is equal to minus 1, where this change of slope happens at omega equal to 1. So let's try to summarize this in this way. So let me take this figure here. This is my current figure. Let me print this as a PDF file that should work. I am actually sort of improvising a bit here, and that's going to be Bode a minus 1 dot PDF. And so this is the one, and this is instead the other one that now is my new current figure. I call this Bode a minus 10 dot PDF, and I hope that this works. So let's go back in my notes, and I'm going to let's see if I can include a figure. Here it is how you can add a figure here. In the meantime, I have converted the PDFs in a PNG, and so this is the one with the parameter a equal to minus 1 that we can import. Oh, this is actually a much nicer way of giving you notes so that I don't have to draw. And let's add another figure here, the one with a equal to minus 10. I'll try to have them roughly the same size, and oops. And now we can start making a comparison. The comparison here is that this point here is omega equal to 1, and this point here instead is omega equal to minus 10. Of course, this is a equal to minus 1, b equal to 1, c equal to 1, and this instead is a equal to minus 10, b equal to 1, and c equal to 1. So the main difference is where this slope happens. In this case, it happens at a certain omega equal to 1, and here we have multiplied by 10 times the parameter a, and this change in slope happens, this knee happens pretty much at 10 times the frequency, omega equal to 10 times the frequency, as opposed to the other case when a was equal to minus 1. And another thing that happens here, at least in this case, is that we have a reduction in amplitude, because now the amplitude here was one, at least for low values of omega, was pretty much 0 decibels. 0 decibels means no amplification, and instead minus 20 decibels means that you are going to reduce the power of your signal by 10 times, so by a factor 10. So these are the main differences when we are modifying the parameter a. Let's see what happens if we modify the parameter b. So we are going to do the same analysis, just keeping a constant. So we are going back to our MATLAB session, and we are going to close all the figures. I'm going to remove all the variables, and I'm going to reinitialize things. And this time I take the standard case, that is minus 1, b equal to 1, c equal to 1, and d equal to 0. I still add the Bode plot, that is the same, it's absolutely the same that we had before. And what I'm going to do is to make for example, C 10 times bigger. If I make C 10 times bigger or B 10 times bigger, no big change, because the effect is going to be exactly the same. I create a new figure for new comparison, and I am going to plot this other Bode diagram. So this is the standard one with the parameters that keep the standard values, and here the change is definitely less radical. I'm going to put this in the notes as well. You can see that the phase is absolutely identical. What has happened is just a change in magnitude. We have 20 decibels more in magnitude because we have increased by 10 times the parameter C. If we had amplified B by 10 parameters, the effect would have been the same. So let me put these figures in the notes for you so that I don't have to draw them. And so this is exactly the same figure that we had before, but now I call this Bode with C equal to 1. And now I'm taking this other diagram and I'm going to call it C equal to 10. And we are going to insert this in our notes. So we go in our notes here. I add the figure. Let's see if this is the correct one. Yes, this is the correct one. So this one has as parameters as A equal to -1, B equal to 1, C equal to 1, and D equal to 0. So it's exactly the same standard case that we had before. And this is the one that we obtained by making C 10 times bigger. So in this case, we have that A is equal to -1, we kept it the same, B is equal to 1, C is equal to 10, and D is equal to 0. Okay, here, the only difference that I want to point out is that we have, because C is 10 times larger when we are going to consider the when we are going to consider the our magnitude, because we have a logarithm, and maybe I forgot to say when in dB we obtain, probably you have seen dBs in other class, we obtain dBs when by taking a quantity and computing 20 logarithm quantity g and computing 20 logarithm of g, and the logarithm is in base 10. So if we make C 10 times bigger, the logarithm is just increased by 1. We multiply that logarithm by 20, so we have 20 more dB. So this is the only difference, and instead the phase is identical. You can see this clearly from the expression that we had. Sorry for moving so fast. From the expression that we had here. Your gain, that is given by CB divided by the square root of a squared plus omega squared, the denominator stays constant, the numerator goes up by 10 times. If you make C or B 10 times bigger, this increase gives you one more bell, when you take the logarithm in base 10, you have one more bell, and you multiply that with 20, so you have 20 more decibels. Okay, at least if you consider the power. Okay, so this is the change of what happens when we are modifying the parameters b and c. So when in summary, when we multiply, we have b and c have the effect of just changing the magnitude of the Bode diagram without affecting the frequency at all. And the change instead in A is a little more delicate. It has a change in the amplitude, in the magnitude that we have, but also has a change in the omegas at which you have your change of behavior, your change of slope in the amplitude, and your switch from a phase that is roughly 0 to being minus pi half. In both cases, it happens at two different frequencies. So A has this double effect, changes something where things are happening on the omega scale, and also changes something about the amplitude if you are modifying A only. Instead, B and C have a visible effect only on the amplitude, with just one exception. We have always considered A and B and C as positive quantities. What I'd like to do here is what happens if C is equal to minus 1. So just an observation, what happens if C is equal to minus 1, or equivalently if C times B is less than 0. What happens in this case? Let's go back to our Bode plot. We can close this too, and let's go back to our definitions. Instead of having C equal to 10, we make C equal to minus 1, and now we go with the Bode diagram. Look what has happened here. In this case, everything seems pretty much the same, but the phase has changed. The phase has changed radically, I'd say. Well, we'll talk about this in a second. Let me just bring this in our notes so that I can draw on it. Let me close this here. Here we have our nodes. I'm actually going to take this thing here and copy it here. Oops. I copied all the thing I didn't want to copy. I'll grab all of it. Yep, it didn't happen. Okay, I'll just import it in the standard way. We still consider our case when C is equal to 1. Resize it a bit. So this is, just to remind you, the standard case: A equal to minus 1, B equal to 1, C equal to 1, and D equal to 0. And now I'm going to report the other case that we have just computed. Where A is stable, B is equal to 1, and C is equal to minus 1, and D equal to 0. So in this case, the amplitude is the same because the absolute value of C is the same in both. So the amplitude is the same because the absolute value is the same. But what changes is that in this case C times B is positive, and in this other case C times B is negative. So let me stress this as much as I can. In this case C times B is positive, and in this case C times B is negative. That's the main difference. And what has happened here is that you have a phase that starts from roughly 0 and goes to minus pi divided by half. Here instead the phase starts from 180 because it's negative, so you have this situation where if you go back to our expression here, if this is negative, you can modify this quantity here, and we'll do that in a second, by taking the absolute value of CB and modifying the phase of phi by a 180 degree shift. Let me do this in this way. So as you can see, everything is the same. Everything is the same here, but the phase has changed. Okay, the phase has changed, and the reason is that if you take CB that is negative, implies that C times B divided by the square root of a squared plus omega squared cosine of omega t plus phi, in the way that we had computed before, actually can be written as absolute value of CB square root of a squared plus omega squared cosine of omega t plus phi plus pi. So the new phase, the actual phase, if C times B is negative, the actual phase shift is arctan of omega divided by A plus pi. And here we have explained why instead of moving from 0 till minus 90 when we use MATLAB to compute the Bode plot, what we observed instead is a shift from 0 plus 180, so from pi in radians, up to 90 instead of minus 90, because if you have minus pi by 2 plus pi, it becomes pi by 2, and so this is why we need to pay attention to the sign of the parameters C and B when you are computing the Bode diagram, because if you have something that is negative, when you're computing the logarithm of the magnitude, you're taking the logarithm of the absolute value of the magnitude, and the information about the sign is instead in the phase shift. So I think with this thing we can close our class today, and so next time we are going to introduce the Laplace transform.